Thank you. So yeah, I just have a few more slides on some of our research, and then we'll get into the hands-on session. So the last thing I really want to talk about is optimizing for NUMA machines. So for all my examples, I start with a problem. So this one is, if you look at machine learning, there's a very large class of problems where essentially they boil down to, I have a bunch of data, those are my yi's, and I want to minimize x according to some function, where x is essentially my output model of that data. And the way you do this is called stochastic gradient descent, where because there's so many y's, you kind of randomly sample y. You compute an approximate gradient at every step that gives you an estimate of the next value of the model, and you repeat this and repeat this and repeat this until x stops changing. So essentially what you have here is billions of very tiny iterations. And the question is, how can you do this efficiently? So if you think about how modern big machines look, this is how they actually look under the hood. Like, I know they tell you that it's all shared memory, communication just works magically, and while it does work, it is not very fast. So in reality, if you have a multi-socket machine, every socket has some number of cores, and then some piece of your total system RAM directly connected to it. And across sockets, you can only communicate through QPI, and then there's a cache coherence mechanism that maintains the caches on all the sockets and the RAM across all the sockets. And the moral of the story is that when you cross sockets, things get slow. So how are we going to solve this problem that I just talked about? Oh, wait, sorry, one more thing. The high-level bit is that if you want the algorithm I showed you to run quickly, there's sort of two areas you could optimize. One we call is the hardware efficiency, which is sort of the time per iteration, right? In order to make time per iteration go down, I can parallelize. I can have a lot of cores working on at the same time. But in order for that to actually scale, of course, I need very infrequent communication. My cores can't be communicating frequently, or things stop scaling. Then conversely, there's what we call statistical efficiency, which essentially boils down to the number of iterations it actually takes to converge. And this, unfortunately, is in direct conflict with when I first said, because the more often you communicate, the faster you converge, the less often, the slower you converge. So now time to converge is the product of those two, and I've just told you that if you make one go up, you make the other go down, so finding the actual optimal solution is very hard. So if we look at some of the trade-offs we could do here, think, well, how are we going to run this? So one we call per machine, which is, and this is the very simple shared memory approach, where you have one version of your model. It sits in some piece of RAM. You just randomly pick which one. And now every core in this machine is operating on that same model. And that model is mutable, so they're all doing writes to that model in parallel. And the cache coherence mechanism of the machine is magically making this work for you. But of course, all the writes to, when you make writes in socket 1, that evicts lines in socket 2, and vice versa. And there's a lot of hardware overhead that goes into making this work. So stalls. So then the other kind of extreme here is, well, let's just make a separate model for every core. And now, of course, you have no contention, because every core has its own copy of the model. Everything's private. The parallelization is going to be beautiful. There's no synchronization even required. But because the models are there's no inter-model communication, they're not updating themselves, you're not going to converge very quickly. So as I said, the infrequent communication means slow convergence. And now there's a trade-off we can make here and say, well, actually, communication within multi-core on one socket is pretty fast, right? We have a shared cache. It's actually not a big deal to do conflicting writes so that it doesn't actually go very far. So the sort of the hybrids approach is per socket, where now we're going to have one model for all the cores within a socket, but we're going to have separate models across sockets. And then so that's our trade-off space, and we're going to run some apps and see what happens. And this is what happens. And you see, unfortunately, there is not one answer. It depends on your app, and it even can somewhat depend on your data size. So as you see, this is the convergence time. And for Gibbs sampling, we have per core and per socket are similar, but poor core is ultimately the winner. SVM, it's per socket. Logistic regression, it's per machine. So here we see is basically that, if you want performance, optimizing your algorithm really matters. And now I want to show you, OK, well, some smart people did this, and they came up with the right algorithm. So what kind of performance can you get if you actually write this in code? And so we compare here to an application called Dim-Witted, which is basically an implementation of what I just told you in C++. And they got a lot of press because they're 100x faster than everyone else who's done this before. And the reason is because they did the very smart things I talked about by limiting communication across sockets and getting very good scalability. You'll see that they're the blue, and they're getting basically 4x on 4 sockets, which is they're essentially linear speedup. But now look at the absolute numbers, and you see that we're even faster than them. And the reason is because we're equally scalable, but our single thread performance is much better than theirs, because we have this great meta-programming generative approach that generates very efficient code, and they wrote C++ they actually wanted to be able to read. So that cost them something in performance. So here we have, OK, you have an algorithm. The optimized implementation really matters, because we're talking about a difference of over 50x here. And finally, I want to direct your attention to this last bar on the right, the GPU. So if you sort of do your back-of-the-envelope peak calculations, you'll think that the GPU should have done way better than this. If you look at the amount of bandwidth this machine has versus the amount of bandwidth the GPU has, in the perfect magic world, the GPU should have been really close to the 48 CPU bar. It should have been way up there. But because Gibbs sampling is essentially a graph application that does a lot of random reads, and as Kunle mentioned earlier, random reads do not go well in the GPU, it is very hard to get anywhere near peak. And so correspondingly, the GPU suffers. And so Kunle showed you an app where the GPU just destroyed the CPU. Now I'm showing you one where the GPU does not do that well. And so the takeaway here is the right hardware matters a lot. You can't just say, all right, GPUs are the way to go. Let's just write code for that. You can't just go for CPUs. It's really, you got to pick the right algorithm. You got to get the right implementation, and you have to find the right hardware for your program. And this is why we think Delite is important, because you don't want to rewrite everything every time to do all this. So I'm going to go into some scalability results for you, but first I want to show you sequential performance. A fun takeaway is scaling is easy when you start out in a hole. Never trust anyone's scaling results that don't show you where they started from, because there's been some very interesting work lately showing, there's a lot of distributed frameworks out there that, we scale out to hundreds of machines and we get amazing speedups. But what they don't tell you is that how much faster or slower they are than sequential C code. And so why should I use 100 machines if I can write a C program that doesn't even need threading and do it in one machine? That's got to be better. So this slide is basically to prove to you that with Delite, we can actually, so this is sequential Delite versus sequential C++. And the C++ is as hand optimized as we could think of. And this is to show you that we are in the right ballpark. That sequential Delite, after we generate code and do our optimizations, is in fact very close to what a smart C++ programmer would write. I use the term smart loosely, of course. And the main difference, if you see we are on average a little bit slower, the main difference is currently that the imperative C++ very aggressively reuses memory. And because we are a functional paradigm, we still allocate a little more memory than we strictly need, and this costs you something. All right, so now I've convinced you we start in the right place. I'm going to show you that we keep going. So the first two apps here are triangle counting and PageRank. And so this is compared to PowerGraph, which is one of the more popular graph analytics engines out there today. And they have reasonably good performance compared to a lot of their competitors. And you see that actually on one thread, its performance is pretty similar. But because they don't account for NUMA issues like I talked about, they stop scaling once you get off one socket. Whereas since we account for NUMA, we keep scaling. And so once you're up to 4 sockets, which is the 48 thread count there, the difference is around 5 to 10x. And of course, it's less than 5 to 10x at one thread. The difference here is really scalability. And similarly, I have some machine learning and data querying apps that we compare to Spark, where once again, Spark is sort of the, the thing everyone talks about, and they do decently well on machine learning type applications. So once again, you'll see that, at one thread, where I showed you Spark results earlier that showed we were like, in the 2 to 3x range over Spark, right? But now you'll see that, well, when you really look at the scalability, we start 2 to 3x, but you start going to massive machines, and it's getting ridiculously huge. So in this, these data querying apps, we're getting like 30 to 45x. And this is in part due to the fact that we have a better data representation than they do, in addition to just lower level code. And in the machine learning apps, it's down to about 10x. And that's because in these apps, the data layout is essentially the same, and so it's only the code gen that matters here.
These are all labeled speed up. Speed up over what?
Over ourselves at one thread. Yeah. Yes. Is that helpful?
And NUMA means after ML compiling
Yes.
via Delite
Sorry.
to NUMA?
So thank you for that, clarifying that. So there's three bars of us and 1 bar of our competitors. So the blue and the red are Delite / optimal not using NUMA optimizations. And you'll see that some cases it just stops scaling, and in some cases on the right it actually gets worse. And the difference between pinning and no pinning is, in no pinning we literally just launch a bunch of threads and let them run. And in pinning we have the OS actually tie a thread to a core. But we don't do smart memory tricks. And then finally, NUMA is Delite optimal with the extra NUMA stuff that we've added, and that's the one that is scaling well. And then Spark is purple, and PowerGraph is light blue. Yes?
Also have a question. So you talk about these single thread base cases that you use as the basis for comparison. So, and you show runtimes. Did you ever consider for those that are computational to calculate performance?
Well, unfortunately, none of these are really computational.
The k-means? And
K-means is kind of on the border.
The k-means, the regression, PageRank, that right?
So PageRank and a lot of these apps actually do very little compute per memory operation. K-means is actually one of the more compute-intensive ones. But other than that, they're pretty memory bound.
But so if they're memory bound, then one can do the same game, but in essence try to assess, I mean, not always, but one can try to assess the minimum amount of data movement that's necessary, and then use the memory bandwidth kind of as the peak that is achieved.
Yes.
Kind of in this roofline plot style.
That.
The only thing I'm saying this is because when you say something like, oh, these C++ programmers, and they really optimize it, I mean, as I argued also in my presentation, it depends very much what kind of program it is, right? So I mean, if the program still, if it's computationally heavy, and it still looks kind of like a normal code, and not like long, bigger, and uglier, most likely it's also not very fast.
Yeah,
it's all relative, right?
I agree. It's the notion of manually optimized code is mythical, right? It means nothing. But I have to show you something.
It just would be nice to see how much headroom there is in one way or the other. And I know it's difficult for some things, but
yeah. So it depends on sort of how regular the memory access is. Because if it's a regular memory access, you're much likely to get close to the peak bandwidth. And if it's not, you kind of just be way off. What you might get.
But this you can take into account. For example, if you know if it's irregular, right? You have a waste because you load entire blocks, but you use only one element, right?
Yeah.
This roofline business takes this into account, right? It just would be, I don't know, it's difficult. What would be helpful to see, like, is the code already reasonably? How good is the code?
Yeah.
I mean, it's good, but the question is it very?
How far?
How much would be possible if
no, the point well taken. And I know you've done some work on the roofline. We're able to kind of bound some of these more.
You can measure, and so the roofline framework gives you some ideas, but there are various ways of doing it.
I agree. That's
Just a comment.
a good way of presenting the data. I can tell you just by my experience that like a lot of these, say like this one and this one and this one, they essentially are streaming through linear memory, and we are maxing out, like, so nothing really fits in cache, so you're basically limited by your main memory bandwidth. And we are getting pretty close to peak on that.
But in just as I would be really helpful in, I think, to make a kind of a roofline here, even if it's back over here.
Sure.
So, but maybe one other point is also, so I'm not sure about these applications, but for example, the MSM builder that we showed. So this is actual C++ code we took from other groups at Stanford who implemented this. I think that's also a matter, okay, to what level of optimization will people actually go? I think it's also valuable to take that as a point of comparison.
Yeah, I'm
Right.
not saying it's meaningless. It's just me
But
as
the
a
point is-
performance
is very
person.
different.
I'm just always curious to see, like, you do a good job, but
How good should it be?
is there still headroom, or are you done practically, right? Because also this
Mm.
informs you whether there's maybe some things you might be missing. in your
Yeah.
narrative framework.
No, I totally agree. Yeah, as Tarek said, there is validity in saying that, like, that whether you can argue that their code is not very good, but it is what they wrote, so that kind of, and we assume that they're relatively smart people, so it's at least what people are willing, the effort they're willing to put in, without spending months and months on it. But yeah, point taken. So. Were there more questions about this graph? Okay, so that is the end. And I would just like to wrap up by saying, so at PPL, we have a few faculty members, Kunle, of course, Pat Hanrahan. We're collaborating with Martin. He does great Scala stuff for us. And all the ML stuff I showed you related to NUMA was actually originally done by Christopher Ray. And then that was the dim-witted thing I showed you, and we ported it to Delite. There we are, a bunch of students. Oh, Jarek has moved, but close enough. And when this slide was made, he was still at EPFL, what do you want from me? And finally, I would just like to say, re-hit some of Kunle's points that if you're going to be power limited, you can't just rely on your CPU to get faster and faster anymore, right? You need parallelism and specialization. That's the only way that you're going to keep scaling. As I think has been hit on many talks here, is that one of the good ways to actually make productive DSLs is through staged embedding, and that with DSLs we can actually get high productivity for the user and high performance by using this common infrastructure. And finally, because of staging and because of Delite, building each DSL becomes incremental rather than like, oh crap, I have to build a whole other compiler from scratch. And then finally, you can get high performance execution through staging to remove abstraction, through these fancy rewrite rules I talked about, through domain-specific optimizations, and finally through like architecture-dependent mappings for GPUs, et cetera. And if you do all that, you actually have a chance of running high-level programs really well on multiple architectures. So thank you. Any questions? OK. So that concludes the formal part. Now, OK, quick show of hands. Who got some horrible error trying to install Delite? OK, that's less than I feared, so that's good. Chark, did you raise your hand? Oh. Okay. So, how many people? Okay. Yes. Questions.
Remark, I just installed Delite, and it seems to assume that you have Python 2 as default, so that might be a problem for some people. Right?
It's Python 2.7, I believe.
Yeah, so there are a lot of Python scripts that just call Python, but if it's Python 3 by default, then you will get problems.
Oh, yes. Thank you. That is.
But that's easy to work around somehow.
You add Python 2 to the top, but yeah, sorry about that. Any other pressing issues or? Okay. So, can anyone read that? All right. Can anyone who's not in the first two rows read that? Okay, well. Ugh. Sorry, need to undo this maximization thing. That's as big as it wants to go. Oh, there it goes. Why is it not? Any of it? Okay. Better? Worse? Good enough. 2 more? Don't know why the shortcut doesn't work. All right. So sort of in this demo, I want to show you sort of how you can build DSLs in Delite, how you can run applications, debug them, and then essentially go into any burning questions you have. So I want to motivate the first part of this by, you've seen a lot of LMS code this week, and you saw that, and while I think it all makes sense, there is this kind of issue where the staging has a price, and that is like the amount of things that you have to type. So just for an example, I've opened up Boolean ops, which is just a part of the standard LMS library that lifts Boolean operations. And what you'll see is that this file actually only defines 3 things. It defines negation and an or, but you'll also see that it's 100 lines long. So let's look at all the things you have to do, which hopefully you're familiar with most of this already. So the first piece we have here is just this is essentially the syntax that you want, but I want to call it using infix notation with ampersand. It forwards to this method, and this method is abstract, returning a rep. And as you know, since we have this abstract rep layer that is different from the rep of t equals x to t layer, you need 2 different traits, right? So now this trait does well, now we're actually in the x world. So now negate is defined to create an IR node that represents negation. So of course I have to define that IR node. And then in order to make transformers and other optimizations work properly, I have to explain to LMS how to make a copy of that node. That's what this mirror method is. Now I might want to write some optimizations. So here's very standard pattern matching. So like a negate of negate is itself. And and of false is definitely false. Very simple things right here. And finally, I have to emit code that represents all these operations. So for Scala, I have codegen, and then for C, I have codegen. And I've helped myself a little bit by saying that this is actually C-like things, and that CUDA, OpenCL, and C are all C-like, and they inherit the same codegen. But the point is that, once again, we defined 3 things, and this took a while to write. So, but it's also very boilerplate. And if you kind of learn the pattern, you can do it very easily. So obviously, the solution is to add another layer of abstraction. That's the solution to all problems. And so we have a meta DSL called Forge, which essentially lets you declare your DSL with much less syntactic overhead, and we auto-generate this file. So now I would like anyone who's following along to, hopefully you have a searcher, to open up something called simple vector DSL.scala. It's in Forge source examples.
Could you show us the forge for the file that you just showed us so that we can see what the reduction is like?
Yes, I can. Oops. Okay, this is it. So you may not be able to read this, but it's definitely shorter. So here I've just defined infix operations, negation, or and, their type is over booleans. And then for my cogen, I have some strings that represent that. And then I've sort of meta-programmed out that, well, in fact, the Scala, CUDA, and C cogens are all the same, so I just loop over them.
But the information like that and or false is false.
Yes, that is not in Forge. So Forge generates the, essentially the API, but everything but the optimizations, and then you add those after.
Okay.
So so going back, the one piece that is not covered here is this, but everything else I showed you in this file is automatically generated.
Okay.
But then after you generate that file, you can open up manually a new file and write these manually. And the reason we did this was basically we couldn't figure out a more succinct way of doing pattern matching than Scala already had, so we figured let's just do the Scala thing. So now, one thing I kind of want to emphasize is there are a lot of ways. We kind of want to make DSLs easy to write and easy to compose. And so we essentially, in a perfect world, DSLs would be as easy to use as libraries, right? If you want a bunch of them, you just import them all and you mix them together, and things work out. And so in Forge/Delite, we do have a limited version of that, in which case, essentially, so my DSL here is called simple vector, and right now it imports Scala ops, which is just like primitive arithmetic, booleans, basic features of Scala that you probably want. And then the actual thing it adds, which is vector operations. So now I want to extend this DSL to do matrix operations. And so now I'm just going to say that, well, now this DSL is not just vectors, but it's actually vectors and matrices. And here I will define what matrices actually are. So my strong recommendation for using Forge is, as we said, to steal and cheat heavily. So I have vector ops, so why not just see what they did and copy it? That's the way you do all coding, right? And for those of you who get really lost, you'll see in the same directory I have given you the solution. So if things go horribly wrong, you know how to copy paste, I hope. All right. So the first thing we need to define is basically our type. So types have two components. One is the user-facing type that everyone sees, which was called vector, and now we're going to call matrix. And it is parameterized over a single type T. And now the other half of that is actually how you implement that type. And so data types in Delite, LMS, Forge, whatever you want to call it, are limited to essentially structures of arrays and primitives. And so data is sort of how you declare a structure. So you'll see, I should call that matrix. I'm going to say a matrix is a struct that has a num_rows field, which is an int, a num_calls field, which is an int, and a data, which is an array. And so now we just need some operations to do on this data structure. So the first thing it would be nice is if we could actually create one of these things. So continue to steal. And now let's sort of look at what this line says. So static here is, there are multiple types of methods. There's the two main ones or actually three main ones. There's static, which is which means that you call the method on the object. So in this case, vector static apply is like a constructor in Scala, right? You would type vector open parens, pass the thing in. And then the other two are infix, which is an infix method, and compiler, which is essentially a private to the compiler method that you need, but you don't want to expose to your users. I'm going to say that I can create a matrix by giving it, in this case, two ints, a num_rows and num_calls. It will return me a matrix of T. And now you see this very interesting little line here. So as has kind of been hinted in the previous talks, in LMS, everything is considered pure unless you declare otherwise. And similarly in forage, every operation has no effects unless you declare them. And the thing you want to be careful of is that if you write something with effects but don't declare the effects, bad things will happen. So in this case, I'm declaring that I want to create essentially an empty matrix thing, and I want it to be mutable so that I can write to it. So that allocates a matrix, which has a constructor. So 0 was our first entry, then $1, which is the other entry, and then finally we fill it in with we allocate an empty array. And this is actually the product of the two sizes. All right. So now I can allocate them, but I can't do anything with them. So the first thing I would like to do is design some basic ways of accessing the fields. So the next thing I want to add is this quick little trick here. So basically, we have this syntactic sugar where everything you define inside this scope here, automatically, it's kind of like having your method in a class instead of in the object. So everything outside it assumes that the first argument to the function is always the matrix, where everything inside this assumes that the self or the this is implicit. So essentially, everything you put inside the matrix ops is kind of like a method on class matrix, and that there's always the this thing that's available to you. So let's see, what do I want? So let's get a few things. Let's get basic getters for the fields. So now this first one I've labeled compiler, which, as I said, means that I want to be able to get the array out of the matrix, but I don't want anyone else to be able to. And it is a function that goes from no arguments to an array of t. And so getter is a special method available on structures that essentially accesses the fields you declare. And of course, this must be one of these fields up here, or you'll get an error. And let's make a public method that allows you to read the, so let's not call it that, the rows and the columns, which is once again, a function of no arguments is a getter, hello. And similarly for columns. Really? So now this is part of my API. Users can ask what the num rows and num cols is, and the way I implement that is just by reading the fields out of the backend data structure. All right. So now that we have that, yes.
Shouldn't the return type of num row be an integer instead of an array?
Thank you. This is why I have people watching me. That is exactly correct. These should return ints. Yes. This is why the solution is available. So when I screw it up, we can cheat. All right. So now, similarly, I want to define apply and update methods, which will allow me to access data elements. So apply takes an int and goes to a t. And now you'll see this new kind of thing, composite. So composite is basically a node I want to implement in terms of other nodes that already exist. The other side of that would be a cogen node, which is something I want to implement as a string. So essentially, when I say apply as a composite, I just mean it's very much like, you know, a method that calls other methods. And so I can do this by calling, array apply of matrix raw data of the self pointer. And similarly for update, I know writing things is considered bad, but we're going to do it anyway. So that takes, and no one caught that one. Matrices are usually indexed by 2 ints. And so this is math. These are things I don't want to write. All right, which just says that, I've essentially flattened the array on the back end, so I need to do some index arithmetic to access the logical value. And similarly for update, let's do a little more. So what's interesting here is, once again, you see that because update is effectful, I need to add this effect annotation that says I'm actually writing to the matrix. And so so a question we get sometimes is sort of what happens when you forget these annotations. And a few things happen. So first of all, if you forget the mutable annotation and then you try to write to that structure, LMS will complain that you're writing something that's not declared mutable. So that one's relatively easy to catch. The effect write one is a little bit harder. So in general, we can't tell, there's no way to prove that what you implemented does a write. But we have a trick which basically says that, anything of type unit is probably effectful, otherwise it does nothing, obviously. So if you follow the convention where any mutable operation always returns type unit, we can catch these as well. And basically we'll give you a warning that says you have something that returns nothing and has no effect. What are you thinking? But on the other hand, if you happen to have update return a non-unit value, there's really no way we can check that, and you're just going to get bad results. All right. So, so apply, update, all sounds good. And now I want to show you how, let's do something that's actually parallel and gives good performance. So let's do matrix addition. So that goes from a matrix of, takes another matrix of T, returns you a matrix of T. And there's actually 2 ways of writing this. And I'll kind of show you quickly how that looks. So the first version you can do is kind of the shorthand version. You can say here that plus on a matrix of T, and where I've limited T to be a numeric type so that I actually know how to add it, implements this construct called zip, where zip directly, of course, goes to a Delite zip with on the back end. And then it's just the function signature is T goes to T, and then the actual thing you want to define of zip is plus. And then the other thing you can write, potentially, that gives you the exact same code at the end of the day is, well, as I said, you can always write composite operations that use things that already exist, and say zip with does exist on arrays already. So you could, read the arrays out of the matrix, zip them, put the array back into a new matrix, and return that. And this is, we've kind of debated on this a lot. I think it's ultimately a matter of taste. This is certainly less verbose, but it does require you to implement some extra API that actually tells Delite how to access your collection. So there's this parallelizes parallel collection thing that basically, if you want to use these parallel operators directly, like map and zip and filter or flat map or whatever over matrices, your matrix collection has to implement this API, which basically says, which tells us how to allocate a matrix and how to write to it and how to read from it. And that's how that really short thing gets desugared in something that could actually compile. And if you write it manually, like so, you don't need that API. So any questions so far? Okay. Yes.
Is it like manual staging of a program? Like instead of having a quote of a program, you
Mhm.
write, you use the operators in the language to define the DSL?
Yeah, so Forge itself is an LMS DSL. But using these constructs, we essentially build a graph of the language, and then using LMS Cogent, we emit Scala code that represents that language. So it's very meta in that way, you know. So one of the things it gives you is the ability to do multiple backends from the same specification. So what you'll see is that not only do you write a lot less code to get something that works. So for example, yeah. So we kind of illustrated this with the Boolean example, but so here's what vector ops would generate from that Forge spec. And it actually continues on into this file. So and then there's more. So this is the implementation, the backend that uses Delite, and there's a second backend called Library, which uses just base Scala, which is mostly used for like essentially debugging and testing your programs for correctness before you want to go through the full compilation phase. So in there you see there is yet another implementation of vector, which has all the same operations, but translates them directly to Scala classes and Scala functions instead of staged things. So now, where was it? Oh yeah. Oh, you can't read that either, can you? Oh. So let me just ask a question here. Like I can talk more about building DSLs in Forge, or we can say that like that's the example and we can talk about something else. Is there a preference in the room?
So what would something else mean?
Well, so the next thing I was going to talk about was actually like what applications and debugging looks like. All right, excellent. Let's move on. This is as I said, like at any time, you just you guys can just tell me like what parts of Delite interest you, and I'd be happy to walk you through it. Because obviously this is less interesting for me, hopefully, than for you. So. All right, so let's just so okay, what you'll see is if you ran the Forge build command on simple vector, you should have a directory here called published, and inside published you should have a directory called simple vector. And now this is essentially the DSL that Forge generated. And now I'm going to show you what an app looks like. So this is hello world in simple vector. So you'll see we have kind of three pieces here. It has, this is the trait here is what you guys have seen previously is the place where ref of t is abstract. And so the benefit of this, of course, is that you write to the API, but you haven't really defined anything, and you can't introspect on anything the compiler does. And then there's this interpreter object, which is where ref of t equals t. And so I know we heard a little bit about this yesterday. The idea that, if once you've abstracted over the embedding process, you can always just, remove it essentially and fall back to Scala. And this is the library version I was talking about, where if you run this version, it doesn't do any magic whatsoever. It just runs as a Scala library. So it's good for, testing your correctness of your code, but not much else. And finally, the compiler version, rept equals expt, where this is invoking Delite, doing staging, generating code. Now, I can do that.
The library version also runs interactively, which is useful.
Yes, oops. Open up a standard Scala REPL. Because it is just a library, it is fully interoperable with all of Scala libraries, REPL, etc. So if I just type SBT console in my DSL, and wait a minute, the REPL is booted. And now I can just try things out, right? So I have vector that was wrong. Damn it. Okay, so now I have a vector with 5 elements. Another vector. I can add them. I can, no, I can't. Nope, can't do that either. It's a very simple DSL. But anyway, you get the idea. Using the REPL, if you're not familiar with the DSL, say like if you want to use one of our real DSLs like Optimal or something, you can open the library version up in the REPL and just start typing things and see what happens. So now if you want to run a real application, where a real I mean hello world. So you see this is the interpreter, which ran pretty quickly. So now I want to generate code. So let's do that. So now you see it says generating program and it finished. And if I open up my generated directory, oops, I see there's this folder called Scala, and then there's a bunch of generated code. Let's find one that's a little more interesting. Yeah, so this is basically what one of our parallel pattern loop turns into in generated code. It's a giant mess that you don't want to read. And correspondingly, you have data structures. And so now if you want, so you always get Scala, but if you want, say, CUDA, you ask for it. If you want C++, you ask for it. And if you want profiling support, which is basically just we add extra instrumentation into the code to enable online profiling, you ask for it. So now my generated directory has some more stuff in it. I've still got the Scala, but I also have some CUDA code, and I also have some C++ code. And what you'll notice perhaps, particularly in the CUDA, is that there were a lot less files for the CUDA than Scala and C. And that's because CUDA can't run everything. So the reason we break our programs down into all these kernel files is that we essentially want to be able to run pieces of your program in different places. So we break your program down into kernels. For every kernel, we try to omit every possible target, but we fail in a lot of cases. And so then once we have, okay, well, for every kernel, these are the possible places I could run, the runtime picks the place you actually want to go, and it manages all the communication to make that work out.
So basically, in the CUDA version, For the missing kernels, it will now take a C++ version.
Yes, right. So we have a graph that says, for every kernel, where can you run? And then, yeah, the scheduling policy is basically, well, if you ask for the GPU, we're going to put as much of the GPU as possible on there. Everything that won't go to the GPU, we're going to run in C++ or Scala.
And it will notice when the transfer overhead is too high and it just does everything on the CPU? Or?
I wouldn't say that that's guaranteed.
But it probably won't.
Sure. I mean, obviously the scheduler is trying to do something smart, but I won't promise that it always finds the right solution. So as Kunle said, you may need some kind of manual intervention in some cases to kind of control what kernels run where. Yes?
Can you hint at how the breaking down into kernel works?
Mm-hmm. It is very, very simple. It is essentially every top-level statement in the program is a kernel. So you'll see that there are a lot of kernels that do nothing, and there are a lot of kernels that do a lot. And so all these sequential kernels get essentially packaged together into one thread and then kind of inline together, and so you don't have a lot of overhead to actually call them. But essentially, if you want performance in Delite, you need to be spending your time in the parallel things and not that sequential random code. So that's, but yeah, there's not any like real magic heuristic. It's just, essentially every parallel pattern at the top level of your program, it becomes a kernel, and then we schedule the kernels.
How do you manage transfer between device and the host code? Is it overlapping transfers and duplication?
Yes. So part of the runtime, essentially, once you decide where things are going, we generate a little piece of code that manages like launching the kernels. And by using the CUDA Streams API, we can actually overlap when we copy data and when we run things. So, all right. So now I want to run this. Oh. Okay, actually, let's do this. So something bad has just happened. If you look at the source code, some lazy programmer read the input args without actually checking that input args were provided. And so, of course, in a non-stage program, you get a nice Java exception that said error at this place, and you figure it out pretty quickly. But normally, like if you've generated code, that error is now in your generated code, not your source code. And there's this fundamental issue in generative programming about how the heck you map errors back to what the user wrote. And so we have a facility for this that's built into Scala called source context that we actually use. And so doing that, you get a slightly better exception which says, okay, well really, the real Java exception was an index out of bounds in this generated code kernel. But then with some Delite magic on top, it tells you that, well, where that code came from was actually in the hello world file at line 12. So hopefully that is useful. It's one of my favorite features. But
Do you only get that nice error handling when running the Scala backend, or does it also work when we are actually running native code?
Any backend. Because the translation essentially happens like from Scala source to generated code, and then like if you get an exception at runtime, we essentially trap the exception and try to figure out where it came from.
But actually, if we have something like, could it happen that we have like an out-of-bounds access and that just goes unnoticed because it doesn't trigger threshold?
So, yeah, like I will warn you that, like, part of in order to be fast, we don't emit like crazy error checking. So in Scala, you tend to get exceptions, and C, you tend to get seg faults. That is an issue. I don't know what to tell you about it. So, oh yeah, back to an actual input. Let's make this a little bit bigger. so you notice that the actually first time you run a Delite program, it's actually compiling all that code we generated. So it takes a few seconds to boot up, but then the second time you run it, that code is cached, so it's much faster. And then we can increase the number of threads we run on with this command. All right, and so that was kind of anticlimactic, right? So let's see what went wrong. Oh, actually. So in order to see what went wrong, I need to run with profiling on. All right. So this is the performance profiler. Not get bigger. So, well, oh, I don't know why it's rendering that way, but you'll see what went wrong is basically, okay, so each one of these lines is a thread, and it didn't get faster with more threads because nothing actually ran in parallel. And so now if we sort of click these things, it will jump to the source code, which is where this op that took forever came from, and we can kind of see where we're spending all our time. And from this, we can say, well, maybe printing everything everywhere is not a great idea for scalability. So let's just comment out some of these prints. And more prints. Okay. Yeah. So then, since we changed the application, we need to go through the full compilation process again. It's faster. That's a good sign. And you see, okay. Fortunately, we're still spending all our time in this one place, and that place is this while loop where we're, sequentially filling in all our vectors. So the key takeaway here is that this is not a good way to write code in Delite. As you may have seen, we are very much encouraging the functional style. And so I'm just going to replace this allocate vector and fill it in sequentially with a bulk constructor. See, I times 2, that was v1. And that goes to I. Let's try one more time.
What's actually in there and what do you actually need to bring somewhere to deploy that code?
In the deg file?
Yeah, so I saw the only file that is the mention here, the deg file that you put on the command line. But actually, I guess I need way more code if I want to deploy that, say, to a number cruncher. I don't want to do the full build on that machine. So basically, do I find a binary somewhere that I can put on our machine and run there, or?
I see. You want to take the generated code, move it elsewhere, and run it later, right?
Exactly. Yeah, I probably don't want to install all that Scala stuff on some machine that runs some.
Right. Sure. Mm-hmm. So there is a way. So actually, if you want to do that, or the trick where you can do where you don't have to always stage main as your entry point, you can stage an arbitrary function, and you do that with calling register function and then the name of it. Let's call it foo. essentially, and I would define a method foo down here. So it has some, type signature. And so if I do that, now essentially the entry point that gets staged is foo, and then we actually emit a normal Scala function or C function as the output. And then so you can take that generated code, call Scala C or GCC on it, and then it's just a binary that you can do anything you want with it. But the yeah. Okay, progress. So let's see. Now, performance has changed somewhat drastically here. It's impressive, right? So you actually notice if you look at this file, like where all the big operations are, say, plus, times, summations, maps, reduces, group bys. They're all parallel patterns, and as we talked about, we can do pretty aggressive fusion. And so when you wrote it this way, by doing this like mutable fill-in vector, like Fusion couldn't figure out that was safe to fuse. But now that you've done it in the functionalized style, this whole program is fused down into 2 loops. And so not only have you made things more parallel, but you've very significantly improved your absolute performance. And so now the kind of last weird thing is this. So does anyone have thoughts about why the heck it runs, like, essentially why the parallel part starts so much later than the rest of it? It's kind of non-obvious unless you really understand JVMs. So the answer is that I'm running a really short program, and JITs have to warm up. So if you, for example, see, I run this once, and it takes, yeah, we really need to make this bigger, first of all. A little bigger. All right. And now I run it, say 5 times. It gets faster, right? And so now let's go back to one thread for a comparison point of view. All right, so now good things have happened. Single threaded takes a little over 2 seconds, and then 4 threads was taking like 0.8 seconds, which is like 2.5 speed up. Or if once you let the JIT warm up, it takes 0.6, which is 3 point something. So there are 2 things you can do. One is to write a real program that takes longer, and the JVM will do pretty well on it. The other thing you can do is just run this in C, because who needs a JIT? Whoa. That did not happen before. Oh, yeah, sorry. Some of our some of the profiler code is new and needs some robustification. So first time, 0.6 seconds. So now we've gotten over 3x speed up on 4 cores, so clearly something good has happened. And you see, yep, it's parallel the whole time. All right, so now we've made a fast application. And I'm ready to take questions. No questions.
Wrote the C code run? Could you let the C code run like that?
Yeah, but do you think anything's going to change? Or
No, maybe with caches, but no. Aside from that.
yeah, so I mean, one thing I'm not fully accounting for is page faults, right? So the reason Java speeds up on multiple runs is JIT plus the fact that all the page faults have already happened because the memory has been allocated. So yeah, I mean, but I don't expect significant differences. That was not the right command. So about the same. All right, well, that is the end of my demo. So
So do you guys have any questions for Kevin then? Any last questions? We have one time. Yes?
About this profiling, how do you decide where to put these profiling points? It's just the whole, profile the whole thing, or
we do profile the whole program. It's so it's part of it is essentially based on the kernels. We wrap every kernel in a timer, and part of it is sampling based. So actually, thank you for bringing it up. I wanted to. Oh, the C is not going to.
because I see these breakpoints around some different phases.
Mm-hmm. In the profiler?
Yeah.
I forgot the profile flag again. All right, so which pieces?
And these different things that different pieces, but it isn't, right? So because, for example, this bar is this kind of thing using this thing.
So the spaces are when that thread is idle.
Okay.
And then the little lines are basically kernels that were too small to render.
So if entrant, it's not.
Mm-hmm. Yes, this is so actually this bar at the bottom represents the start and stop of your program. So you can kind of see that my program started very quickly. The first thread started, nothing happened for a while. It got parallel, everything shut down. And then this part here in blue is actually the memory usage you're doing. So you see it kind of goes up and up and up, and then it stabilizes. And we do this by actually like using callbacks into the JVM to periodically poll the state of the heap, and then that's sampling based, and then we report it to you in this graph. So one of the things performance issues you'll often encounter when you write functional programs, say like because something didn't fuse properly, is that you use a lot of memory. And so you can really see here that like, wow, in this kernel, ridiculous garbage collection has happened, that's why it's slow.
Regarding that profiling tool,
Mm-hmm.
is that yours or is there some other project that it just happened to adapt to?
No, we wrote it in-house. I didn't personally write it, but
Okay.
it's...
Because it actually looks pretty cool.
Yeah, thank you. It's so it's the pretty part, the JavaScript is an external tool,
Okay.
but our tool essentially did all the profiling and then put it into this essentially graph format JavaScript engine, and then that renders into the cool looking piece.
Okay.
Is that D3? Or?
It is D3, yes.
All right, any other questions? All right, I guess it's time to thank Kevin then. Thank you very much.